Chapter 1 Energy. Hello everyone, today we begin our journey into mechanics by exploring one of the most fundamental concepts in physics, energy. Historically, humans have always found ways to harness energy from our ancestors using gravitational potential energy to release heavy stones, to the use of elastic energy in buoys and arrows. In this lesson, we will decode the different forms of energy and understand the law that governs them all, the principle of conservation of energy. Let's start by watching a short introductory video.
Welcome to The Explainer. Today, we're diving into Chapter 1, building a complete, fascinating picture of energy concepts. So, ever wonder where energy actually goes when a moving object stops? Let's figure it out together. It all starts with stored power. Think about our ancestors using elastic potential energy to hunt with bows. We also store energy through gravity. Picture water held high up in a massive reservoir, ready to drop. So, on a large, macroscopic scale, we're mainly dealing with gravitational and elastic potential energy. When that stored energy is finally released, bam! It transforms into kinetic energy, the energy of motion. Now, this motion can be translational, flowing in a straight line, or rotational, like a spinning turbine. Add those macroscopic, kinetic, and potential energies together, and you get a system's total mechanical energy. But wait, what actually happens when these moving objects hit resistance, like everyday air friction? Take a falling parachute. Gravity pulls it down, sure, but air resistance sharply limits its final speed. Those frictional forces reduce the macroscopic mechanical energy, instantly transforming it into microscopic internal energy. You can think of internal energy as hidden heat at the atomic level. Invisible, but incredibly real. Add a system's mechanical and internal energy together, and you found its absolute total energy. Like the mathematician Poincare noted, in an isolated system, this total amount of energy never actually changes. And if a system doesn't exchange energy with its surroundings at all, it's perfectly energy isolated. For these isolated systems, any loss in mechanical energy exactly equals the gain in internal energy. We've covered the core concepts, but to wrap up, let's quickly lock in those essential formulas. Here is your complete, screenshot-ready cheat sheet, pulled straight from the chapter summary. This maps out everything we just discussed, from kinetic equations to the total conservation of energy. So, since total energy is never truly lost, how are you going to transform yours today?
Concept 1. Macroscopic mechanical energy, EM. First, let's look at energy. We can see at macroscopic level, mechanical energy is divided into two main types, kinetic and potential. Kinetic energy is the energy of motion. If an object is sliding, it processes translation kinetic energy calculated as Ek equal half mv squared. However, if it's a solid rotating about a fixed axis like a turbine, it has rotational kinetic energy expressed as Ek equal half I theta prime squared, where I is the moment of inertia. We can solve this application for memorize and understand the concept and the formula of kinetic energy. A density of mass m equal to kilogram slides without rolling on a plane with a speed v equal 3 meters per second. Calculate its kinetic energy. In this exercise, we have only kinetic energy of translation. Ek equal half mv squared. B. The disk D of radius r equal 50 centimeter rotates about a fixed axis with rotational speed n equal 4 turns per second. In this part of exercise, we have rotation. Ek of rotation equal half I theta prime square. In this equation, we have two unknowns, I and theta prime. I equal half mr square and theta prime equal 2 pi n. Potential energy. We have potential energy, which is energy stored due to position or configuration. Gravitational potential energy when an object is an attitude z. It stores energy relative to the reference level EP equal mgz plus EP0. Elastic potential energy EPE. When we stretch or compress a spring by a distance x, energy is stored within it. The formula here is EP equal half kx square. We have another application for more understanding. Application 2. A body of mass m equal 10 kg is at a point A of altitude 20 meter above ground, g equal 10 meter per second square. 1. Calculate the work done by the weight of the body when it moves from A to the ground. The equation of work W equal mg za minus z0. 2. By choosing a reference level for gravitational potential energy, calculate the gravitational potential energy when the body is A at the ground level, B at A, C at point B, 30 meter below A. The equation of gravitational potential energy is mgz. For z equals 0, EP equals 0. For z equal 20 meter, EP equal 2000 joule. For z equal minus 10 meter, EP is negative, minus 1000 joule. Another application for elastic potential energy. A spring elongates by 5 cm under the action of a force of 100 Newton. A. Calculate the force constant of the spring. Hooke's law gives F equal Kx, K equal 10 over 0.05 equal 2000 Newton per meter. B. Calculate the energy needed to elongate the spring by 20 centimeters. The required energy W is equal to the energy stored in the spring. W equal and W work equal E energy equal half Kx square equal 40 joule. The sum of kinetic and potential energies gives us the total mechanical energy of the system. EM equal EK plus EP. Internal energy U. Physics is not just about what we see on the outside. Every system has internal energy U at a microscopic level. This energy comes from two sources: microscopic kinetic energy and microscopic potential energy. The random thermal agitation of particles, which increases with temperature, is microscopic kinetic energy. The bonding and forces between particles, which changes during physical phase like melting, is the microscopic potential energy. The total energy E of any system is the sum of its mechanical and internal energy, E equal EM plus U. The very important concepts is the energy as isolated systems and conservation. Let's talk about a critical concept, the energy isolated system. A system is isolated if it does not exchange any energy with its surrounding. In such a system, the total energy remains constant. E equal constant. The total energy is constant. If there is no friction or chemical reaction, then the mechanical energy itself is conserved. Em equal constant. Delta Em equal 0. Application 4. A dart gun is made up of a spring of constant K equal 250 Newton per meter. The dart of mass M equal 25 gram compresses the spring by a distance of 6 centimeters. Calculate the launching velocity in the case of a horizontal shoot. Neglect friction. For solve this application, we have two states. State 1 at x equal a, and state 2 a equal 6 centimeters, and state 2 at x equal 0. The friction is negligible. Therefore, Em1 at state 1 equal Em2 at state 2. Therefore, we can calculate velocity v equal a radical k per m. However, if friction is present, mechanical energy decreases, while internal energy increases by the same amount. Delta Em equal minus delta U. Energy is never created or lost. It only changes form. To summarize, energy is a quantity conserved under different modes of transfer. Whether we are looking at a failing parachutist experiencing air resistance or a sample pendulum, the principles of energy allow us to predicate motion and understand the universe. Now, let's move to the exercises to apply these formulas and test your understanding.